When it comes to concrete structures, engineers sometimes say, if it isn't cracked, it isn't working. Sounds incredibly counterintuitive, right? But it highlights a fascinating reality about the very foundations of our built world. Today we're taking a deep dive into that surprising reality, the hidden language of concrete cracks. This deep dive is based on a really meticulous research paper. It's titled Reasons of Cracks in Reinforced Concrete Structures, Methods of Repair by Dr. Issam Melhem. This paper is basically our guide today to understanding why cracks appear, what they truly tell us, and crucially, how experts approach their diagnosis and repair. Our mission today for you is to unpack the language of these cracks, understand their numerous causes, and discover how experts figure them out and fix them, giving you a powerful shortcut to being truly well-informed about something most of us just will walk right over without a second thought.
It's absolutely true. Cracks are often seen as this inherently bad sign, something to immediately panic about. But understanding them allows us to distinguish between, let's say, normal, expected structural behavior and actual serious problems. And making that distinction matters immensely for the long-term durability, the aesthetics, and, well, most importantly, the safety of our structures. It's really about knowing what's a symptom of normal life versus a genuine health concern for a building.
Okay, let's peel back the layers then on why these cracks actually appear. Our source tells us they're super common, but the reasons are incredibly varied. Some are absolutely not a big deal, others definitely are. What's truly fascinating here is just how many factors can contribute to a simple line appearing in concrete even before any weight is put on it.
Exactly. The fundamental concept really is that economically designed, reinforced concrete structures inherently experience what we call tensile stresses. Think about it this way. Concrete is fantastic at resisting compression, being squashed, but not so great at resisting forces that try to pull it apart, tension. That's why we embed steel reinforcement, the rebar, to handle those pulling forces. This inherent difference in strength means some level of minor cracking is often an expected part of its behavior, not always a cause for alarm.
Okay, so some cracking is almost designed in a
Yeah.
way.
You could sort of say that. It's anticipated.
Mm.
Let's start with what we call non-structural cracks, the everyday cracks you might see. First, we have plastic shrinkage cracks. These occur very shortly after concrete is poured as the surface water evaporates too rapidly. You'll often see them in hot, windy conditions or under direct sun exposure. They look like short, shallow, random cracks, typically not longer than, say, 700 millimeters in unreinforced slabs. They often show up in these crisscross or random patterns while the concrete is still in its plastic wet state.
So these are almost immediate then, before the concrete even really sets hard, like tiny stretch marks forming as it settles.
Precisely. That's a good way to think about it. They're usually just on the surface, cosmetic, not deep structural issues. Then there are drying shrinkage cracks. Now, these are about the volume change in concrete as it dries and hardens over time. This isn't directly related to any applied loads. They're very common in buildings. Several factors influence how much this shrinkage occurs.
Like what kind of factors?
Well, things like an increased cement content per unit volume or a higher water to cement ratio, basically, more water in the mix. Also, the use of very fine materials like sand, which, require more water. And the environment matters too. Low humidity during curing, like if concrete is stored in dry air, causes more shrinkage than in humid conditions. And critically, a large surface area to volume ratio. Think thin slabs and walls, they shrink faster than massive structures like dams.
So it's almost like baking a cake too much water, wrong ingredients, maybe drying it out too fast, and you get cracks. Is that a fair analogy, or am I oversimplifying things?
No, that's actually a very apt analogy. It captures the essence quite well. And the practical implication of this drying shrinkage is that these cracks can cause significant tensile stresses and, yes, visible cracks, especially if the concrete cover over the rebar is either too thin, say, less than 4 centimeters, or surprisingly too thick, maybe over 10 centimeters. It really highlights the precision needed in concrete work.
Interesting that too thick can also be a problem.
It is. It relates to stress distribution. Now, next up, thermal shrinkage cracks. These are generated by the heat produced during cement hydration. That's the chemical reaction as cement mixes with water and hardens. Especially in large concrete elements, the temperature inside can rise significantly during hardening, and then it falls as the concrete cools down to the ambient temperature. This contraction, this cooling, causes tensile stresses.
Right, so big temperature swings, even internal ones, can really stress the concrete. What about chemical reactions, maybe from the ground it's sitting on?
Absolutely. That leads us to cracks from sulfate attack. These happen when concrete interacts with sulfates, which can come from the soil or groundwater. Sulfates react with certain compounds in the hydrated cement paste, forming expansive products. These cause high localized tensile stresses, leading to the concrete deteriorating and cracking over time. It's like a slow internal chemical expansion pushing things apart.
Wow. And then you mentioned steel.
Yes, and this is one of the most critical ones, corrosion of reinforcement steel cracks. This is when rust forms around the rebar, the steel bars inside the concrete. Rust is expansive, it takes up more volume than the original steel. This expansion puts immense pressure on the surrounding concrete, which leads to longitudinal cracks appearing along the rebar's length. Eventually, this can cause the concrete cover to spall off, basically pop off, leaving the rebar exposed.
Then I imagine moisture and certain chemicals would speed that up significantly, like near the coast.
Precisely. The presence of chlorides, for instance, which is common in coastal areas with salt-saturated air and humidity, greatly accelerates this corrosion process. The implication is severe. Corrosion significantly reduces the effective cross-sectional area of the rebar, compromising the structural integrity. It's particularly critical in pre-stressed concrete, where the steel is already under high tension. Any reduction in its cross-section is extremely dangerous there.
So it's really eye-opening to see how structures can crack just due to their very nature, the materials, the environment, even without anything heavy sitting on them. But when does that normal behavior, that breathing, as some call it, turn into something more serious? When should we genuinely worry that a crack signals a deeper structural issue?
That's the core question, isn't it? The normal cracks we just discussed, the non-structural ones are one thing, but those that truly signal structural issues, those demand immediate attention and proper assessment.
Okay, and here's where it gets really interesting. Our source meticulously breaks down these structural cracks into three key phases of a structure's life: design, construction, and service. It's almost like a forensics report for buildings, tracing the problem right back to its origin. First up, cracks due to structural design errors. So these are issues that originate way back on the drawing board or maybe in the calculations. They can stem from simple numerical or calculation mistakes, perhaps data entry errors when using design software, or maybe just a lack of proper review before the plans get approved. It's actually surprising how a tiny miscalculation early on can have massive consequences down the line.
Indeed. Or it could be something broader, like an improper structural system selection. This happens when the chosen system isn't really suitable for the loads or the situation, perhaps due to a lack of sufficient engineering experience or sound judgment in that initial design phase. Another common design error is incorrect load assumptions, maybe failing to properly account for specific loads like wind or earthquakes, or just misjudging how weight will be distributed. Imagine designing a roof that can handle rain, but completely forgetting about the potential for heavy snow loads in that region.
That makes perfect sense. So beyond just the overall design concept, can the actual specifics like the rebar details in the design mess things up too?
Absolutely. A very common design flaw is specifying insufficient reinforcement steel, the rebar. This means either there isn't enough rebar specified in total, or it's detailed incorrectly, maybe where it should stop or how it should be distributed, or using the wrong diameters in critical spots. This leads to high stresses in the steel and excessive elongation, which causes visible cracking in the concrete. Even poor detailing of how bars connect or overlap can create weak points.
So design is clearly a huge factor. But even if you have a perfect design, things can still go wrong during the actual building process, during execution, right? It feels like there's so many potential points of failure.
Precisely. That brings us to the next category: cracks due to execution or construction errors. These happen on site. A significant cause here can be issues with the foundation soil specifically, discrepancies between the actual soil properties found on site and those that were assumed back in the design phase. You might build on what you think is firm ground, but if it's actually softer or different, problems arise.
And water seems to be a recurring theme. Is it a problem during construction too?
Oh, definitely. Faulty plumbing or maybe poor site drainage during construction, leading to water leaks, fresh or saline, permeating the foundation soil. That's another common construction error that can lead to settlement and cracking. And sometimes, honestly, it's as simple as ignoring the detailed plans and specifications, maybe relying solely on personal experience or perceived shortcuts instead of following the engineer's instructions.
What about the temporary stuff, like the molds they pour concrete into?
You mean the formwork? Yes, poor formwork practices can also contribute significantly. This could be neglecting to clean wooden formwork properly, which can affect the concrete surface, or removing it too early before the concrete has gained sufficient strength to support itself. Formwork are those temporary molds that shape the wet concrete, right? And if you strip them too soon, the concrete isn't strong enough, it sags or deflects, and cracks form. For example, our source mentions removing formwork from cantilever retaining walls and then immediately backfilling behind them too soon that can lead to distinct longitudinal cracks.
And rebar issues aren't just about the design of the rebar. They can be construction problems, too, like putting it in wrong.
Exactly. Using rebar that doesn't actually conform to the project specifications, maybe the wrong grade of steel, wrong yield strength, incorrect diameters, that's a construction error. Or, very critically, providing insufficient concrete cover. That's the protective layer of concrete over the steel. If it's too thin, the source suggests less than 2.0 centimeters for beams and columns, or less than 2.5 centimeters for exposed slabs. The rebar is vulnerable.
Okay, so the steel needs proper protection. What about the concrete mix itself during construction?
Right? Myriad issues can arise with poor concrete placement practices. Things like segregation, where the components of the concrete separate during pouring because it was dropped from too high, or maybe transported improperly. Or honeycombing, due to insufficient vibration helps consolidate the concrete, remove air voids. Without enough, you get these pockets of air and coarse aggregate instead of solid concrete. Using non-conforming mixes, maybe too much water added on site, or neglecting proper post-pour curing, keeping it moist so it hardens correctly. These are all major issues. Even getting the dimensions wrong, discrepancies between the executed size of a beam or column and what was actually designed, that can lead to problems. And finally, a big one, the simple but often overlooked lack of proper quality control, like skipping required lab tests to confirm the concrete's properties, its compressive strength, absorption, workability, things like that.
Wow, okay, so many ways things can go wrong during construction. It really highlights the complexity and the need for good site supervision. And then, even once a building is successfully built and up and running, it's still not entirely out of the woods. Things can happen during its life.
Exactly. The third category our source identifies covers cracks due to utilization or service errors. These are problems that arise during the structure's operational life, how it's used or maintained. Probably the most common is unplanned modifications, people making unauthorized changes to structures, or converting buildings for purposes other than their original design without proper assessment. Say, changing a residential building into a public assembly space, or an industrial facility with heavier loads. The structure might not be designed for that.
And I imagine just neglecting maintenance, like ignoring leaks, would fall into this category too.
Yes, absolutely. Tolerating water leaks, whether it's fresh water or saline water, maybe from pipes or roofs for extended periods, that moisture can severely compromise the structure over time, leading to corrosion, material degradation, and ultimately crack formation. It's often a slow but steady attack.
Okay, so we've talked a lot about why cracks happen, design, construction, use, even just the nature of the materials. Now, how do we actually read them? What does a crack's width, its shape, or its location tell an engineer? It really does sound like learning the unique fingerprint of a structural issue, almost like being a building doctor reading an X-ray looking for subtle signs with potentially huge implications.
That's a perfect analogy, actually. The characteristics of a crack, its width, its depth, its length, its pattern, they provide critical clues about its underlying cause and its severity. And that ultimately defines its significance regarding both durability and aesthetics.
So what's the first thing you look at? Width.
Crack width is usually a primary indicator, yes. It can be estimated visually, just by looking, or measured more precisely using specialized optical devices or crack width gauges. Precision isn't always paramount, though. The key is often knowing if it's less than or greater than certain critical thresholds. Think of it this way. Very fine cracks, the ones less than maybe 0.1 millimeter, are usually just barely visible and often not a major concern for durability initially. But as they get wider, say, approaching half a millimeter or more, that's when we start seeing accelerated issues like water ingress and corrosion becoming much more likely. It's really that visible discontinuity that signals a potential pathway for deterioration. Our source indicates that once cracks exceed about 0.4 millimeter or 0.5 millimeters, corrosion and rebar deterioration can really start to accelerate rapidly.
Okay, so the width is crucial. But what about where the crack appears? Do different parts of a building, like columns versus beams, show different typical crack patterns?
Oh, absolutely. The location and the pattern of a crack can tell you a lot about the forces at play. Let's look at columns, for example. If you see horizontal cracks in a column, they might indicate significant eccentric loads, meaning the load isn't applied neatly through the column center, causing bending or perhaps insufficient confining reinforcement that ties. Also, a single horizontal crack, or maybe several, accompanied by signs of foundation settlement, could point to movement underneath.
What about vertical cracks in columns?
Vertical cracks, on the other hand, often signal problems with excessive axial loading, maybe coupled with low concrete quality. Sometimes they're related to concrete shrinkage, too. They can also be a telltale sign of rebar corrosion, especially if they appear at the corners, maybe with concrete spalling off and visible rust stains. In some cases, specific patterns of vertical cracking can indicate internal chemical reactions, like an alkali aggregate reaction, where certain minerals in the concrete itself swell up over time, literally pushing the column apart from the inside. It creates a kind of map cracking. The severity of vertical cracks often relates to how the internal ties, those small hoops of rebar that hold the main vertical bars in place, are spaced. If they're too far apart, the column is weaker.
Okay, columns make sense. Now what about beams, the horizontal elements holding up floors?
Right, for beams with normal reinforcement, not pre-stressed, you'll typically see what we call flexural cracks. These are usually vertical or near vertical. They appear due to the maximum bending moments, particularly in the midspan area where the beam tends to sag the most under load. Incline cracks, however, usually diagonal ones, appear due to maximum shear stresses. Those are forces trying to slice or slide one part of the beam relative to another. These shear cracks are often found near the supports towards the ends of the beam.
And what causes those inclined shear cracks specifically?
They're often caused by things like low concrete shear strength or maybe inadequate shear reinforcement, meaning the stirrups. Those small loop-like pieces of rebar that wrap around the main bars are spaced too far apart or there aren't enough of them. Poor detailing, like improper welding of the main longitudinal rebar and the transverse stirrups, can also contribute. Our source notes that cracks wider than, say, zero point 0.5 millimeters in beams usually indicate significant issues, like overloading or perhaps insufficient main longitudinal rebar to handle the bending forces. It's a clear red flag needing investigation.
Got it. And finally, slabs, the floors and roofs, which are everywhere we walk and live. What do their cracks tell us?
For slabs, particularly roofing or floor slabs, crack patterns are really related to how the slab's supported, its static scheme, the type of load it carries, the reinforcement method used, and even its aspect ratio, how square or rectangular it is. As a general rule, cracks typically form perpendicular to the direction of the principal tensile stresses, the main pulling forces. If you see cracks widening over time, it often means overloading insufficient main rebar, or maybe incorrect rebar placement during construction, for instance, if the rebar mesh got pushed down too far towards the neutral axis, making it less effective. If these cracks exceed about 0.3 millimeters, the source suggests additional reinforcement or strengthening is almost certainly needed.
Do top and bottom surface cracks mean different things?
They often do. If you see cracks on the bottom surface of a slab, especially if they run in one or two directions and are accompanied by rust spots and maybe some concrete spalling, that's a pretty clear sign of rebar corrosion. Water has gotten in from below or maybe through the slab. Top surface cracks, however, can have different causes. Random, map-like cracking with some surface crumbling, especially in cold climates, might be due to freeze-thaw cycles damaging the surface layer. In dry regions, top surface cracking might be more related to drying shrinkage, or perhaps poor quality materials used in the finishing layer. Very fine hairline cracks on the top surface might just indicate thermal stresses from temperature changes.
That's just an incredible amount of information we can glean just from looking closely at a crack. It really is like a building whispering its secrets, isn't it? Yeah. But okay, once we've listened, once we've figured out what the crack is telling us, what do we do about it? How do engineers actually go about healing these structures?
That's the critical next step, you're right. Knowing the cause and the type of crack is only half the battle. The next, equally important part is determining the most effective method of repair. Because as we've seen, a crack isn't just a crack when it comes to deciding on the right fix.
Exactly. And our deep dive highlights that repair isn't just about slapping some patch material on it. It's a careful, multi-step process. It starts with detailed observation, almost like a doctor doing a follow-up visit before prescribing treatment.
Absolutely. Step one is almost always crack monitoring, especially if there's any doubt about the cause or if the crack seems serious. Methods can range from the simple, like putting plaster telltales over the cracks to see if they break or widen, to using more sophisticated displacement gauges or crack monitors that measure movement precisely. The goal is simply observing if the crack width increases or changes over time. For suspected structural cracks, measuring the overall deflection or deformation of the element, or even foundation settlement using fixed reference points might be crucial. The key determination engineers must make from this monitoring is whether the crack is active, meaning its width is changing, maybe with load cycles or temperature fluctuations, or if it's dormant, meaning its width has stabilized and remains constant. This active versus dormant distinction is absolutely critical because it fundamentally dictates the entire repair approach.
Okay, that makes sense. You wouldn't use the same treatment for a stable scar as for a wound that's still changing. So once we know if it's active or dormant, that tells us what kind of repair method to select.
Precisely. Step 2 is selecting the appropriate repair method. This choice is heavily based on whether the crack is active or dormant, and crucially, what the main objective of the repair is. Are we trying to restore the original structural strength? Are we just trying to prevent water leakage and improve durability? Or is it mainly about aesthetics? The goal informs the method. Step 3 then covers the actual repair techniques themselves. These are broadly categorized into structural repair, which aims to restore or even increase the load carrying capacity, and non-structural repair. Non-structural repair focuses more on simply filling the cracks to prevent moisture ingress, or maybe repairing spalled areas and treating corroded rebar to protect it from further damage.
Okay, let's start with the small ones, those hairline cracks we talked about. What's the typical approach there?
For hairline cracks that are deemed non-structural and dormant, the repair might be relatively simple. You typically clean the surface thoroughly, maybe with a wire brush, then apply something like cementitious adhesive layers or specialized coatings just to seal them off. If they happen to be a bit deeper, even if narrow, and run perpendicular to compressive forces, the source suggests they might sometimes be carefully injected with low viscosity, perhaps heat curing, products like certain epoxies to bond them.
Okay, what about the bigger ones, the wide cracks? Especially if they involve problems like rust.
Right, for wide cracks, the approach depends heavily on that underlying cause we diagnosed earlier. If the crack is associated with rebar corrosion and rust is clearly visible or suspected, then the damaged concrete cover must be removed to expose the corroded steel. The rebar then needs to be thoroughly cleaned, usually by mechanical means like grit blasting, sometimes treated with corrosion inhibitors, and potentially supplemented if section loss is severe. Then, the area is repaired with good quality concrete or a specialized repair mortar, often using techniques like hand patching, form and pour, or sometimes using high-strength sprayed concrete, known as shotcrete, or perhaps adhesive resin grouts for strong bonding.
And if the wide cracks aren't primarily due to corrosion, but maybe due to something more fundamental like overloading, settlement, or just poor original concrete.
That's a critical point. If the wide cracks stem from other causes like overloading, foundation settlement, poor concrete quality, or insufficient rebar in the design, then the underlying cause must be addressed before or concurrently with the crack repair itself. Simply patching the crack won't solve the root problem. The repair might involve removing and replacing the defective concrete, maybe adding a new layer of concrete bonded with epoxy glue to strengthen the section. In many cases, additional reinforcement steel might need to be added, perhaps anchored into the old concrete using epoxy mortar to make up for the original deficiency or handle increased loads. It's like you wouldn't just patch a hole in your roof if you realized the whole foundation was shifting. You had to fix the foundation first, right?
Absolutely. Now, you mentioned epoxy earlier. Is epoxy injection a common technique for structural repair?
Yes, epoxy injection is a very common and effective technique specifically for structural repair of dormant cracks. Its purpose is to essentially glue the cracked sections back together, restoring structural integrity. Epoxies used for this typically have high compressive strength and develop a very strong bond to the concrete. It's generally used for cracks that are relatively narrow, often those not exceeding maybe 0.5 millimeters, though formulations vary. The process usually involves drilling small injection ports or inlets at intervals along the crack, sealing the surface of the crack between the ports, and then injecting the low-viscosity epoxy resin under pressure using a specialized pump, filling the crack completely.
That sounds incredibly precise, getting the epoxy right into the crack. What about using more flexible materials for repair? I imagine you wouldn't always want something super rigid, especially if there might still be some minor movement.
That's a good point. Flexible materials are another important category of repair products. These are often organic polymers. While epoxy binders are very common for achieving high-strength structural repairs, other polymers like polyurethanes are also used. Polyurethanes tend to be more flexible than epoxies. There are also thermoplastic polymers like acrylic binders, which can be fast setting, but the source notes they can have high shrinkage in dry conditions and might not adhere as well to concrete as epoxies or polyurethanes. The primary use for these more flexible sealants is often for sealing cracks, simply to prevent water leakage, especially in situations where some minor movement might still be expected, or in constantly saturated or humid conditions. They act more like a flexible gasket. Sometimes cementitious materials, like special types of Portland cement or quick-setting cements, are also mixed with organic polymers to create hybrid grout materials.
Okay, interesting. And finally, there's a technique I've heard mentioned that sounds exactly like what it is. Stitching, like literally sewing the concrete back together.
Pretty much. The stitching method is another structural repair technique used specifically to restore tensile strength across a major, typically dormant, crack in a concrete section. The procedure involves drilling holes on both sides of the crack, perpendicular to the crack line. Then you clean these holes thoroughly. Next, you insert U-shaped metal staples, often made of rebar, with short legs bent at each end. These staples bridge the crack. Finally, these staples are anchored securely into the drilled holes using a high-strength, non-shrink grout or sometimes an epoxy adhesive. It's important, as the source notes, to potentially reduce the spacing between these staples near the ends of the crack for better effectiveness. It literally stitches the two sides of the crack together mechanically.
It's truly incredible how engineers can analyze these cracks with such detail and then essentially heal a structure using these different techniques. It sounds like it takes a huge amount of precision and knowledge to get it right.
Indeed, it really does. It requires a deep understanding of the materials involved, how structures behave under load, and, critically, diagnosing the correct root cause of the problem. There's always more to learn in this field, and applying this knowledge correctly is absolutely key to ensuring the long-term safety and serviceability of our built infrastructure.
Well, you've now seen how concrete cracks are far, far more than just surface imperfections. They are vital clues, really a silent language spoken by the very buildings and bridges around us. We've explored everything from those common, often harmless shrinkage cracks that are just part of the material's nature, to the much more serious structural issues that can be caused by errors in design, construction, or how a structure is used over its life. And we've seen how experts decode the messages these cracks send through their width, pattern, and location, and then apply sophisticated methods to monitor and repair them. Our source paper, Dr. Melham's work, concludes with some really key recommendations for preventing and managing cracks in the first place. First, it stresses implementing all necessary design measures and precautions to minimize cracks right from the start, always considering the specific nature of the loads the structure will face. Second, simply using good quality concrete is essential. The paper mentions not less than C20 grade as a typical minimum, referring to its compressive strength. Third, ensuring sufficient concrete cover for the rebar is critical for protection, remembering those minimums, like 2.0 centimeters for beam columns, 2.5 centimeters for exposed slabs, and never less than the rebar diameter itself. Fourth, conducting regular and thorough monitoring of structures throughout their life. Mapping any cracks that appear and identifying their causes and widths is vital for early intervention. Fifth, it emphasizes that engineers must possess precise scientific knowledge to accurately assess crack causes and properly evaluate their impact on structural safety. It's not guesswork. And finally, a practical point. Always test repair materials in a lab before using them on site to confirm they actually meet the required specifications for the job. So maybe the next time you walk past a concrete building or drive over a bridge, you might just look at it a little differently. Perhaps with a newfound appreciation for the hidden stresses it endures and the clever engineering diagnosis and repair that keeps it standing safely. It makes you wonder, doesn't it? What other invisible aspects of our world might be speaking to us, telling us stories, if only we knew how to listen? We really hope this deep dive has given you a powerful shortcut to being well informed about a crucial yet often overlooked aspect of civil engineering. Keep exploring, keep questioning, and maybe keep an eye out for those subtle signs around you that might just tell a bigger story. Thank you so much for joining us on this deep dive.
My pleasure entirely. It's a field full of these subtle complexities, and it's always rewarding to share a bit about how we try to understand and manage them.